Yeah, let's talk about here how can we estimate sums of series, and that's actually an easy answer because you just use partial sums. But then also how close to the actual value of that series have you found with whatever partial sum you use? So that estimating sums of series, that's what we're going to talk about. Okay, so if we've got a series and it converges, okay, we let two, I don't know that we've used S before, but let's, what we do is we let S represent the sum of the series. So it converges to a number. So we're just going to call that number S. So let S be the sum of the series. And we did talk about S sub n, or what S sub n was. That's just the nth partial sum. So if we wanted the 10th partial sum, S10, that just means all the terms up to the, till you have 10 terms. Okay. All right, well, what, one thing we can say is, one thing these partial sums can show, you know, if you start writing them out, S1, S2, S3, S4, I think we did that maybe for one of them, and we showed that the limit did not exist. But if you take the limit of the S sub n's, partial sums, as n goes to infinity, so if you, one way is just write them all out and see, are those partial sums going to something? That's the hard way to do it. Well, I would say the hard way, but the other way, just evaluating it. So if you look at the limit as n goes to infinity of the S sub n's, if you can figure that limit out, that's the S, that's the sum of the series. So one way to figure out what this series is, sums to, what it converges to, the S, is by doing this limit. In practice, that's pretty difficult to do. So the next best thing is to estimate the sum by just using a partial sum and figure out how close you got it, okay? Or how close you need it, and then figure out the partial sum off of that is another way to go. All right, so how do we do that? How do we figure out if I use an nth partial sum, say the 10th one or whatever, 20th one, how do I figure out, well, how close did I get? A lot of times that's the kind of answer that you're looking for. Well, here's how I do it. Let's write out, so S is the sum of the series. So S, let's just write them out term by term here, just to start out and go where I'm going to go with this. But so you got A1 plus A2 plus A3 plus A4, starting at n equals 1. But does it S ever stop? No. We're talking about usually n equals 1, but whatever n starts, it's going to infinity. So S continues out to infinity, right? But it converges, so there is a number that this equals, and that's what we're trying to figure out. Now, on the other hand, if I do the S sub n, the difference between it and S is S sub n stops, right? A sub 1 plus A sub 2 plus A sub 3. S sub n only goes out to the nth term, or yeah, the nth term. Okay? Well, here's the deal. S contains S sub n because the A sub n term is out here. It's just that it doesn't stop there, it just keeps going. okay? So there'll be another term after that, another term after that, infinity. All right, well, I write it that way because what I want to talk about here is the remainder series. Let's let R sub n be the remainder R sub n. The remainder when you take the s minus the s sub n. That's what's left over, okay? So what would happen if I take the s and subtract s sub n? Well, if I take s and subtract all these terms get wiped out, right? Up to the a sub n, and what's left? Well, a sub 1 out to infinity, right? Okay? So that's what R sub n is. It's just the remainder. It's what's left over when you take away the s sub n from the s. Okay? All right, now, if we have a positive decreasing series, it's possible then to estimate our error or estimate the size of R sub n which, if you think about it, R sub n then is going to kind of be the error that we have when using s sub n, right? Because if I take s sub n away from s, what's left over is what I didn't add in with s sub n. You see what I'm saying? So R sub n is kind of like the error in my using s sub n, okay? And, R sub n is going to shrink whenever I use more terms. But we can estimate the size of that error, R sub n, by thinking about the integral test. Remember on the integral test, we use these little diagrams to kind of help us understand here. All right, so we've got this positive decreasing series, and we related it to this. Remember, f of n was our function. We're talking about a series, and so f of n was the a sub n term, right? So I've got f of x graphed here. All right, now here's what we have to understand. This R sub n, where does it pick up, in essence? It picks up, the R sub n picks up after the nth term. So, I mean, we can go as far out as we want, but let's just say there's our nth term. And so the R sub n terms are going to be out there, all right? Well, remember how we could how can I represent the a sub n plus 1 term? Well, here's n plus 1. Remember how we represented n plus 1? Just go up here and make a little rectangle. This right here is a sub n plus 1. A sub n plus 2, then would be the next rectangle over. Go up to the height there. Yeah, because the height gives me, the value of the term. And the area it's one is the width, and so the height is really what it's all about. But, and then a sub n plus 3 would be over here. Okay, so on and so forth. Now, you see how that's related to the integral. So the little rectangles I've got here represent r sub n. How is r sub n related to this n to infinity f of x dx integral? Looking at the diagram. What's this represent? Area under the curve. It's the area under the curve. So wouldn't r sub n, these terms, be less than or equal to? There you go. That's a way to estimate the error that you have. The r sub n represents the error. So the error is something less than this integral here, n to infinity f of x dx. Okay? It's a way to estimate the error. Okay. All right. So, for example, let's consider 1 over n cubed. A. Approximate that series, 1 over n cubed, using the first 8 terms. Like I said, it's not hard to estimate one of these series because you just do a partial sum. In this case, I'm going to do s sub 8. What would s sub 8 be? Well, we started, if there's no index given, it starts at 1. So the first term would be 1 over 1 cubed. S sub 8 would go up to 8. 1 over 2 cubed, 1 over 3 cubed, all the way out to 1 over 8. Yes? There's an estimate for 1 over n cubed. S sub 8. Wrote it down to make sure. So you got 1 over 1 cubed plus 1 over 2 cubed, 8, plus 1 over 3 cubed, plus 1 over 4 cubes, 4, plus 1 over 5 cubed, 125. $1.195160244 approximately. So that's approximately that sum. Now, let's estimate the error by using SA for this series here. Okay, and so what I'm going to do is I'm going to use this little formula here. The error, which is the remainder that I have, that remainder's got to be less than or equal to that. So here, R8 is less than or equal to the integral n8 to infinity f of x. So what's f of x here? 1 over x cubed dx. So my error is less than or equal to that integral. All right, so what's this integral? It's x to the negative 3. Well, it's an improper integral, so limit as t goes to infinity. That's x to the negative 3, so I add 1, it'll be x to the negative 2. It'll be negative 1/2 x to the negative 2. Evaluated from 8 to t. So that's the limit as t goes to infinity. Negative 1/2 t to the negative 2 minus a negative 1/2 8 to the negative 2. Well, put that in a little better format here. That's negative 1 over 2t squared, and that's plus 1/2 or 1 over 8 squared. 64. So that limit as t goes to infinity, well, t is going to infinity, so I've got 1 over infinity squared. That's 0, there it is. Plus 1 over 2 times 64. So this error, so this, let's recap here. So R8, our error, is less than or equal to 1 over 128. Which probably would mean a little more if we put it in decimal form. So R8 is less than or equal to about, well, it is 0.0078125. So that's how big the remainder is for 8 terms. It's less than or equal to. So this is the most it is. That's the most error it has. So the error is at most 0.0078125. So close to 8 thousandths. We're within 8 thousandths, give or take. Okay. That's pretty good. I mean, it's within 8 thousandths, so it's not going to be too far away from that. All right? Now, let's do one more problem with this one. All right, so let's say that's pretty good, 8 thousandths, but let's figure out how many terms I need for this. A little different twist to it here, the last thing. All right, so C. How many terms are needed to estimate some 1 over n cubed to within 0.000001, 6 places. How many terms do we need to get that accuracy right there? So let's say we needed that accuracy, for whatever reason. Instead of spinning our wheels trying to figure out, well, it doesn't move. It's within that many places. Let's just figure out how many we need and go from there. Okay, well, what I need then is R sub n to be 0.001. So here's our formula. So I need R sub n to be 0.00001. I want that less than or equal to, all right, so in this case, n to infinity. I don't know the n, that's what I'm trying to figure out. So let's just evaluate this integral here, kind of in general. Move it over here so I can expand my writing to the right there. All right, so I've got 0.0000001 less than or equal to n to infinity 1 over x cubed dx. Well, same integral really. I'm just doing n instead of 8. Still be minus 1/2 x to negative 2 and run n to t. So that's the limit as t goes to infinity. Negative 1 over 2t squared minus a negative 1 over 2n squared, right? Skip ahead there. T still goes to infinity, so this still goes to 0. So this integral is 1 over 2n squared. Does that change to positive? So that goes to 0 because t goes to infinity. Yes? So here's what I've got. So I've got 0.001. I need that less than or equal to 1 over 2n squared. Okay? All right. Let's see, I'm doing this backwards here. All right, so to within, okay, so I need, got in there yet. So I need it to be within, so I want r sub n is less than or equal to that. I want the r sub n less than 0.0001. Yeah, this is what I want. I want the r sub n less than or equal, so I shouldn't have put that 0.001 in there just quite yet. Because I want the r sub n within this small amount. So now I know 1 over 2n squared, I want that to be less than or equal to 0.0001. The only thing on these inequalities you have to be careful with is multiplying by a negative, but n here is going to positive infinity, it's positive, so if I multiply both sides by 2n squared, and it's squared too, so, but it doesn't matter the power, it'd still be positive because it's positive numbers. Well, I would say 1 is less than or equal to 0.002 n squared. So divide off the 0.0002. That turns out to be a pretty nice number, actually. 500,000. So less than, that'd be n squared. Well, as you know, 500,000 less than n squared means n squared is greater than 500,000. Which, what does that make n? Greater than, even greater than. Square root of 500,000? Just 707.1. So that n is the number of terms I need. It needs to be greater than 707, so why don't we go 708? So we need 708 terms. Quite a few. We want that much accuracy, but that's what it is. Okay. To ensure within that accuracy right there, we would need 708 terms. All right?